Yeah, hi everyone. Welcome to my Max Academy. In this video, we'll continue with the chapter Relations and Functions, which is chapter number 1 from 12th standard CBSE Mathematics. So we'll continue with some more examples on the types of relations which are reflexive, symmetric and transitive. So we'll continue with some more example. I had given some more example in my previous video you would have watched. Then we'll continue from there. So we'll take the next one, which is the fourth example. I am giving series of example for the better understanding of these three. So we'll continue with the one more example. There is example 4s. Suppose A is the same set. So this is your A cross A. Now I'm going to define a relation R4. R4, name of the relation. I don't want to use R for all the relations. So R4, the fourth example. It is defined as a set of all A comma B such that R4 is defined as set of all A comma B such that mod of A minus B is less than 2. Mod of A minus B is less than 2 for every A comma B belonging to capital A, where A is the set. Fine. So set of all A comma B such that modulus of A minus B is less than 2. Now we need to check whether this relation is reflexive, symmetric, transitive. Whether they are reflexive, symmetric, transitive. So now we will write our R4 in the roster form. This is in the set builder form. Roster form means modulus means absolute value, right? Mod of A minus B should be less than 2. Now let's take each element from A cross A and we will check whichever element in A cross A satisfies this condition, that will come into this set. Now let's take 1 comma 1. 1 comma 1 is 1 comma 1, which means 1 minus 1. A is 1, B is 1. So 1 minus 1. 1 minus 1 is 0. Mod of 0 is 0. 0 is less than 2. Yes. So 1 comma 1 will come, comma. Then 1 comma 2. 1 minus 2. 1 minus 2 is minus 1. If you take this element, A is 1, B is 2. So 1 minus 2. 1 minus 2 is minus 1. Modulus of minus 1 is 1. 1 less than 2. Yes. So 1 comma 2 will come. Then 1 comma 3. 1 comma 3 means 1 minus 3. 1 minus 3 is minus 2. Modulus of minus 2 is 2. 2 less than 2. No. So 1 comma 3 won't come. Then 2 comma 1 will come. Because 2 minus 1 is 1. Modulus of 1 is 1. So that is less than 2. 2 comma 2 will come. 2 comma 3 will come. 3 comma 1 will come. 3 comma 1. So 3 minus 1. If you take this element, A is 3, B is 1. 3 minus 1. 3 minus 1 is 2. Modulus of 2 is 2. So 2 is less than 2. No. So 3 comma 1 won't come. But 3 comma 2 will come. And 3 comma 3 will come. So this is our relation. Now we should check whether this. So whenever they give the definition of the relation or the relation is in the set builder form, you need to convert that relation into the roster form, which means you should start listing the elements if it is possible. If it is an infinite set, then we cannot list all the elements, right? So this is a finite set because we are dealing with A as a finite set and relation R is a subset of A cross A. So A cross A is a finite set. So the relation also should be a finite set. Now we'll check whether it is reflexive. For reflexive, what we should do, check whether you have to take every element from A. For each element in A, the element should be related to itself. Right? A comma A should be in R for every A in A. For every A comma A should be in R. Now let's take 1. Then 1 comma 1 should be in R4. This relation name I'm just calling it as R4. 1 comma 1 is there? Yes. Then take 2. 2 comma 2 is there? Yes. 3 comma 3 is there? Yes. Therefore it is reflexive. So we can say A comma A belongs to R for every A belonging to A. Therefore A comma A belongs to R4. Therefore R4 is reflexive relation. So we have proved because 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there, which means A comma A belongs to R4 for every A in A. Now let's check whether it is symmetric. Now for symmetric, what do we check? If whenever A comma B is there, its reverse also should be there. Whenever A comma B is there, its reverse also should be there. Now let's check that. Now 1 comma 1. The reverse of 1 comma 1 is 1 comma 1. A comma B. If A comma B is in R, then its reverse, which means B comma A also should be in that set. R. Now here R4, 1 comma 1. Reverse of 1 comma 1 is 1 comma 1, which is in R4. Now 1 comma 2. Reverse of 1 comma 2 is 2 comma 1. This is A comma B. A comma B is in R4. Then B comma A. What is B comma A? 2 comma 1. Is it in R4? Yes, it is there. 2 comma 1. 2 comma 1 is there. Now again 2 comma 1 is there. Reverse is what? 1 comma 2, which is there. 2 comma 2. Reverse is what? 2 comma 2, which is also there. And 2 comma 3. Reverse is 3 comma 2, which is there. And next, go to the next element. 3 comma 2. Reverse is 2 comma 3, which is there. Then 3 comma 3. Reverse is 3 comma 3, which is there. So for every element, the reverse, whenever A comma B belongs to R, the reverse B comma A also in R4. So we'll say for every A comma B belonging to R4, B comma A belongs to R4 or implies. For every A comma B belonging to R4 implies B comma A belongs to R4. Therefore, R4 is symmetric. Symmetric relation. Fine. Now let's check transitivity. Now is it transitivity? So we'll take some pair. We'll generally try to find some two elements which is in this form A comma B, then B comma C. Then we have to check whether A comma C is there. For every pair of this, A comma B means the next element should start from B. Wherever the first element is ending, the second element should start from B and then C. Then whenever A comma B and B comma C is in R, we should check whether A comma C is also in R. Now here let's take some elements. Let's observe this. Let's take this element. Let's take this 1 comma 2 and 2 comma 3. Because generally we'll try to choose some elements which will fail. We'll try to get some elements which will fail. If it fails, then we can say it is not transitive. Right? So now let's take this. Now 1 comma 2. This is like A comma B. It is in R. Then 2 comma 3, which is B comma C. It is also in R. So A comma C is it in R? A comma C means what? 1 comma 3. 1 comma 3 is here. No, it is not there. Therefore, it is not transitive. Even if you could find one pair like this, true, but A comma C is not there, then you can say it is transitive. Even if you could find one pair of elements, A comma B, B comma C. Here, 1 comma 2, 2 comma 3. A comma B, this is A, this is B. Here, this is A, this is B. Sorry, B and C. This is B and C. So A comma B is there, B comma C is there. Then A comma C should be there. A comma C means A is 1, B is C, B is 3. Is 1 comma 3 is there in this set? No, it is not there. Therefore, it is not transitive. So, when we are saying that it is not true, we will give one example where it is failing and say that it is not transitive. But if it is true, then you have to write the proof to say that something is true. So here we have checked manually. Sometimes it is easy to check all the elements, and if all the elements satisfy for symmetry, we can say it is symmetric. Sometimes we have to write the proof also. But to disprove something or to say that something is not right, even if you take one such pair where this condition is failing, then that is enough to say that it is not true or it is not transitive. So we'll say 1 comma 2 belongs to, that we call it as a counter example. If you are taking one example where the condition is not true, this condition is not true. If you could find one example where this is not true, we call that as a counter example. That is a counter example to say that this is not true. So 1 comma 2 belongs to R4 and 1 comma 2, then 2 comma 3 and 2 comma 3 belongs to R4. But so this is A comma B, then B comma C. A comma B and B comma C. Then is A comma C. A is 1, B is 2, here B again 2, 3. See, wherever it is ending, A comma B, wherever it is ending, you have to choose another element in such a way that it should start from this 2. This 2 it should start here. This can be anything. Then 1 comma 3. So A comma B is in R4, B comma C is in R4. So A comma C, which is 1 comma 3. Is it there? No, it is not there. But 1 comma 3 does not belong to R4. Therefore, R4 is not transitive. Transitive relation. Okay? It is not. But whereas R4 is both reflexive and symmetric, but it is not transitive. Fine. So let's go to the next one. See, fifth example. Right? I am giving series of examples. It's not your book example numbers. Giving some examples. So let's take one more. Next one is, suppose again on the same set A, we are taking set of all R5. R5 set of all A comma B. I'm just giving the name for the relation R5. You go to set of all A comma B. Set of all A comma B such that A plus B is suppose greater than 4. A plus B is greater than 4 where A comma B belongs to A. Right? So R5 relation is what? Set of all A comma B such that A plus B is greater than 4 where A and B belongs to A. Where A and B belongs to the set A. Now we have to check whether it is reflexive, symmetric, transitive. What it is. Now let's try to write the relation R5 in the roster form. Now which means I should take all the elements A comma B such that the sum should be greater than 4. A plus B should be greater than 4. Let's take this 1 comma 1. 1 plus 1 is greater than 4? No. So 1 comma 1, 1 comma 2. 1 plus 2 is 3. 3 is greater than 4? No. 1 comma 3. A is 1, B is 3. 1 plus 3 is greater than 4? No, it will not come. 2 comma 1? No. 2 comma 2? No. 2 comma 3 will come. Because 2 comma 3, if you add 2 plus 3 is 5. 5 is greater than 4. So 2 comma 3 will come. 3 comma 1 won't come. 3 comma 2 will come. 3 comma 3 will come. Because 3 plus 3 is 6. 6 is greater than 4. So among these 9 elements, only these 3 elements qualify for this condition. Only these 3 elements satisfy this condition. Only these 3 elements will come in the relation R5. Now we have to check whether it is reflexive, symmetric, transitive and all that. Now first one is what? Reflexive. Now reflexive means we'll go to the set A. For every element in A, we should check whether that element is related to itself. Which means if I take 1, then I should find 1 comma 1 in R5. I am taking element 1. 1 comma 1 is there? No. The moment if it, we can stop and say it is not reflexive. Now we'll say 1 belongs to A, but 1 comma 1 does not belong to R5. R5 is the name of the relation. We generally call it as RRR. I don't want to put RRR everywhere. I'm just trying to differentiate this relation and this is another relation, R5. So, but 1 comma 1 does not belong to R. Therefore, R5 is not reflexive. To prove something is not reflexive, we can take one example where it is failing. If you want to prove, then we have to write the statement like this, or we'll have to prove in some problems. Right? So it is not reflexive. Now is it symmetric? Now 2 comma 3. Symmetric means whenever 2 comma 3 is there, reverse also should be there. 2 comma 3. Reverse of 2 comma 3 is 3 comma 2, which is there. Then 3 comma 2. Reverse of 3 comma 2 is 2 comma 3, which is there. Reverse of 3 comma 2 is this is A comma B. A, B, then B, A should be there. B comma A should be there. That is the definition for symmetry. Whenever A comma B belongs to R, then B comma A also should be in R. Now 2 comma 3 is there. The reverse of 2 comma 3 is 3 comma 2, which is there. Again take this element. 3 comma 2. Reverse of 3 comma 2 is 2 comma 3, which is also there. So it is true for okay for this. This is also fine. 3 comma 3. Reverse is 3 comma 3. This is also okay. So for every element, it is true. Therefore, we'll write this statement. So for every A comma B belonging to R5 implies B comma A belongs to R5. Therefore, R5 is symmetric. R5 is symmetric. Because we have checked for each element. Once you check for each element and if it is true, then we can write this definition itself. Definition of symmetric itself. Because you have checked for each element. Now, transitivity. Is it transitive? Now let's take the element. 2 comma 3, A comma B. And we should find an element which is starting with 3, which is this. Now 2 comma 3 belongs to R or R5. Then 3 comma 2 is also there. This is like A comma B. So this is A comma B. This is B comma C. So A comma B is in R5. B comma C is also in R5. Is A comma C, is it R5? This 2 comma 2. Is it there in R5? Right? 2 comma 2 So 2 comma 3 is there, 3 comma 2 is there. Is 2 comma 2 is in R, is it in R5? No, it is not there. So therefore, it is also an example where it is not transitive, because A comma B is there, B comma C is there, but A comma C is not there, right? So it is also similar to this. So where it is only symmetric but not reflexive or not transitive. So we'll say R5, or we'll take the example where it is failing. So we'll say 2 comma 3 belongs to R5, and 3 comma 2 belongs to R5, but so A comma B belongs to R, B comma C belongs to R, but A comma C, which is 2 comma 2, does not belong to R5. So therefore, R5 is not transitive. R5 is not transitive. It's not a transitive relation. Even if it fails for one element, we'll say that it is not transitive. Fine. So 2 comma 3 is there, 3 comma 2 is there, but 2 comma 2 is not there. If you take the reverse way, 3 comma 2 is there, 2 comma 3 is there. If you take this as A comma B and this as B comma C, then 3 comma 3 is there. But if I take in this order, it is not there. 2 comma 2 is not there. It should be true. Right? If I take this element as AB, A comma B, which is 2 comma 3, so the 3 comma 2, AB, then if I take the BC, then AC is 3 comma 3 is there. But that doesn't make that it is transitive, because if it is true for one element, it doesn't mean that it is true for all. You have to check for every pair. But this pair, if I take it in this order, this as A comma B, this as B comma C, then 2 comma 2 should be there, which is failing. It's not there. Therefore, it is not transitive. Clear? Now, let's go to the next example. You can pause the video and take the notes. Let's go to the next example, which is R. Next relation, suppose sixth one, which is R6. We'll define R6 as set of all A comma B, set of all A comma B such that A by B is an integer and A comma B belongs to A. Suppose I am defining one relation, set of all A comma B such that A by B is an integer, which means when I divide A by B, when B divides A, it's an integer means what? A is exactly divisible by B. It's an integer. A by B is an integer. Then, and A comma B belongs to capital A. Now, what is our corresponding elements? So we should check this condition, whether if I divide A by B, whether it is an integer or not. Now let's take this 1 by 1. What is 1 by 1? A is 1, B is 1. If I take 1 comma 1. What is 1 by 1? 1 by 1 is 1. 1 is an integer. Therefore 1 comma 1 will come. Now let's take 1 by 2. What is 1 by 2? 1 by 2 is 1 by 2, which is not an integer. So 1 comma 2 won't come. Then let's take 1 by 3. 1 by 3. 1 by 3 is not an integer. So 1 by 3 won't come. Now 2 by 1. 2 by 1 is what? 2. 2 is an integer. So which means 2 by 1 will come. Then 2 by 2. 2 by 2 is also an integer, because 2 divided by 2 is 1. So 2 by 2 will come. So 2 comma 2 will come. Fine. Then 2 comma 3 will come. So 2 by 3 is not in. So 2 by 3 won't come. 3 by 1 will come, because 3 by 1 is 3. So 3 by 1 will come. Because 3 by 1, 3 comma 1 means A is 3, B is 1. So 3 by 1 is 3. 3 is an integer. So 3 will come. 3 by 2 won't come. 3 by 3 will come. Now we should check whether it is all the three, whether it is reflexive, symmetric, transitive, whichever it is, we have to check that. Fine. So what do we do there? Now let's take this 2. Fine. Now let's check for reflexive. What 1 is there, then 1 comma 1 should be there. It is there. 2 means 2 comma 2 should be there. 3 in A, so 3 comma 3 should be there. So everything is there. 1 comma 1 is there, 2 comma 2 is there. 3. For every element in A, 1 comma 1, 2 comma 2, 3 comma 3 is there. So which means this is true. For every A in A comma A belongs to R. So we can say, or we can even write say 1 comma 1 comma 2 comma 2 comma 3 comma 3, all the three belong to R6. Therefore R6 is reflexive, because for every element 1 comma 1 is there, 2 comma 2 is there. We can write like this also, or we can just write the definition, a comma a belongs to R6 for every a in capital A. You can, and therefore R is reflexive. You can say that way also. Now next one is it symmetric? Symmetric means, let's take 1 comma 1 reverses 1 comma 1, it is there. 2 comma 1 reverses 1 comma 2, it is not there. Therefore it is not symmetric. So we'll say 2 comma 1, which is this, that belongs to R6, but the reverse, which is 1 comma 2, does not belong to R6. Therefore R6 is not symmetric. R6 is not symmetric relation. Clear? Now let's take let's check for transitivity. Now is it transitive? Now let's take this. So now 1 comma 1 is there. Now let's take any element that is starting with 1. 1 comma 1, this is a comma b. So b is 1. I should have b comma c, which means 1 comma something. 1 is not there. So leave this element. Then this is 1, 2 comma 1. Now anything that is starting with 1 again, 2 comma 1, it should start with 1, which is this. So now 2 comma 1, a comma b, again b comma c. Therefore a comma c, which is 2 comma 1, it is there. If you take this as a, b, this is b, c. So a, b and c. Then a comma b belongs to R, which is R6, and b comma c is also there in R6. So a comma c means 2 comma 1, which is there. So it is true for this. Now any other element starting with 1? No. Now take this 2 comma 2. Anything is starting with 2, this one. So 2 comma 2, this is, you take it as a comma b, then b comma c, then a comma c, which is 2 comma 1, it is there. Now any other element starting with 2? No. Let's take this one, 3 comma 1, right? 3 comma 1. Then we'll have to again check element starting with 1. This is 1. So 3 comma 1 is there, then 1 comma 1 is there. Therefore 3 comma 1 is there, which is there. Right? So similarly now 3 comma 3 is there. Anything starting with 3 comma 3, this one. 3 comma 3 is there, then again 3 comma 1 is there. Therefore 3 comma 1 is there, which is right. If you take this as a comma b, then b comma c, then a comma c. A comma c means 3 comma 1. This to this 3 comma 1, which is this, which is there. So for every element it is satisfied. For every element that is satisfied. Therefore we can say it is transitive. So we'll say so a comma b belonging to R6 and b comma c belonging to R6 implies a comma c belonging to R6, right? For all such pairs, or what we can say, for all a comma b comma c belonging to a set A. Therefore R6 is transitive. R6 is transitive. Clear? So it is not only symmetric, but it is reflexive and transitive. Fine. Now let's take one more, 7th relation. Let's say R7. So how do we define R7? R7 will define it as set of all a comma b, set of all a comma b such that a minus b is divisible by 2. A minus b is divisible by 2. We will define set of all a comma b such that a minus b is divisible by 2, where obviously a comma b belongs to a. Now what is the relation for this? Let's take this now, R7. Let's write this, which is in the set builder form to roster form. Now a minus b should be divisible by 2, right? Now 1 minus 1, a minus b, 1 minus 1 is 0. 0 is divisible by 2, yes. So 1 comma 1 will come. Then 1 comma 2, 1 minus 2, is minus 1. Minus 1 is divisible by 2. So 1 comma 2, 1 comma 1 comma 3. 1 minus 3. 1 minus 3 is minus 2. Minus 2 is divisible by 2. Yes. Minus 2 by 2 is minus 1. It is divisible. Therefore, 1 comma 3 will come. 2 comma 1 will come. 2 minus 1 is 1. 1 is divisible by 2. No. So 2 comma 1 won't come. 2 comma 2. 2 comma 2 means 2 minus 2. 2 minus 2 is what? 0. 0 is divisible by 2. Yes. Therefore, 2 comma 2 will come. 2 comma 3 will come, which means 2 minus 3. 2 minus 3 is minus 1. Minus 1 is divisible by 2. No. Then 3 comma 1. 3 comma 1 means 3 minus 1. This element. 3 minus 1 is 2. 2 is divisible by 2. Yes. So 3 comma 1 will come. 3 comma 2 is 3 minus 2 is 1. 1 is not 0. 3 comma 3 is 0. So 3 comma 3 will come. So these will come. Now we should take whether it is reflexive, symmetric and transitive. Now first one is reflexive. For reflexive, 1 means 1 comma 1 is there. 2, A is 2, 2 comma 2 is there. 3, 3 comma 3 is there. Therefore, we can say 1 comma 1 is there in R7, 1 comma 1, comma 2 comma 2, comma 3 comma 3, all belong to R7. Therefore, R7 is reflexive. Fine. Then we will take one more, which is let's check for the second one. Symmetric. Symmetric means whenever 1 comma 1 is there, its reverse should be there. A comma B is there means the reverse B comma A should be there, right? So 1 comma 1 reverse is 1 comma 1 which is there. 1 comma 3 reverse is 3 comma 1 which is there. Then 2 comma 2 reverse is 2 comma 2 which is there. Now 3 comma 1 reverse is 1 comma 3 which is there. 3 comma 3 reverse is 3 comma 3 which is there. Therefore, it is symmetric. So we can say A comma B belongs to R7 implies B comma A belongs to R7. Therefore, R7 is symmetric. R7 is symmetric. Now next one is transitivity. Now transitivity we will have to take the pair and check. Suppose let's take 1 comma 1 is there, 1 comma 3 is there. A comma B, B comma C. Then A comma C, 1 comma 3 it is there. Then let's take this one, 1 comma 3, 3 comma 1. Now 1 comma 3, 3 comma 1 will give me 1 comma 1. If I take this as A comma B, B comma C, then 1 comma 1 which is there. Right, 2 comma 2 there is nothing starting with 2. Then 3 comma 1, anything starting with 3, 1, this one. 3 comma 1, this is A comma B, then this is B comma C. So 3 comma 1, 1 comma 3 will give me 3 comma 3 which is there. So for every pair it is satisfied. So we'll say A comma B belongs to R7, therefore it is transitive. R7 and B comma C belongs to R7 implies A comma C belongs to R7. Therefore R7 is transitive. So here it is all the three. It is reflexive, symmetric and transitive relation. Right? We have one more definition, which is definition number 4. If a relation is reflexive, symmetric and transitive, all the three, then that relation is called as an equivalence relation, which I will do it in the next video. Now, so this is for a relation where it is all the three, reflexive, symmetric and transitive. Fine. Now I'll write one more example, then we will be done with a good number of examples. I'm giving more examples so that you understand how to check reflexive, symmetric and transitive. So we'll go with one more, which is 8th one, example 8. So suppose the 8th relation R8, I'm going to define as set of all A comma B says that A minus B equal to set of all A comma B says that A minus B equal to 1, comma A comma B belongs to A. Now we should check whether it is reflexive, symmetric and transitive. Now first let's try to write this in the set roster form. A minus B, the difference should be 1. Then that element will come here. Now 1 comma 1. 1 minus 1 is equal to 1. No, this won't come. Now 1 comma 2. What is 1 minus 2? Is minus 1. Is it equal to 1? No, it won't come. Now 1 comma 3. 1 comma 3. 1 minus 3 is minus 2. Minus 2 equal to 1? No, then 2 comma 1 is 2 minus 1. 2 minus 1 is 1, so 2 comma 1 will come, right? Then 2 comma 2, 2 minus 2 is 0, so 2 comma 2 won't come. 2 comma 3 is 2 minus 3 is minus 1, that also won't come. 3 comma 1 will not come. 3 comma 2 will come, because 3 minus 2 is 1. Now 3 comma 3 is 0, so only these two elements are there. Only these two elements will come. Now is it reflexive? Now 1 comma 1 it is there? No. 1 is there, 1 comma 1 should be there. 2 means 2 comma 2 should be there. 3 comma 3 should, none of them is there. So we'll say 1 belongs to A, or you can even say 2 belongs to A, but 2 comma 2 does not belong to A. You can take any one of the elements from A. So we'll take 2 also. That's okay. 2 belongs to A, but 2 comma 2 does not belong to R8. Therefore, R8 is not reflexive. Now again, we have to check the second one, which is symmetric. Is it symmetric? Now 2 comma 1 is there. The reverse should be there. Reverse is what? 1 comma 2. Is it there? No. 2 comma 1 is there, but the reverse is not there. Therefore, it is not symmetric also. So we'll say 2 comma 1 belongs to 2 comma 1 belongs to R8, but the reverse A comma B is there, but B comma A, the reverse B comma A is not there. But 1 comma 2 does not belong to R8. No, 1 comma 2 is not. 2 comma 1 is there, its reverse is not there. Therefore, R8 is not symmetric. Right? Then the last one is, we have to check whether it is transitive. Now let's check this. Now let's take this one. If I take 2 comma 1, it is not starting with 1, nothing. So now let's take this one and this one. I will take this as A comma B. See, 3 comma 2 belongs to R8, and 2 comma 1 also belongs to R8, right? And 2 comma 1 also belongs to R8. So this is like A comma B. So A comma B belongs to R8, and B comma C belongs to R8. Therefore, A comma C is what? 3 comma 1. Is 3 comma 1 is present here? No. So it is not transitive. Therefore, it is not transitive. So we have 3 comma 2 belonging to R8, which is A comma B, and B comma C belonging to R8. But this 1 comma 3 comma 1. So A comma B belongs to R8, which is this, and 2 comma 1, that is also in R8 in this set. But 3 comma 1, which is A comma C, which is 3 comma 1, which is not there. Therefore, it is not transitive. So, but 3 comma 1, which is A comma C, right? 3 comma 1, which is A comma C, 3 comma 1 does not belong to R8. Therefore, R8 is not transitive relation. Clear? Fine. So now I have given enough examples to check whether the given relation is a reflexive, symmetric, transitive, which means it can be any combination, can be all the three, the relation can be all the three or none of the three like this, or only it will be symmetric or not reflexive, not transitive, or both symmetric and transitive but not reflexive. All the combination is possible. Fine. So we will stop here, and you can pause the video and take the notes, and you can watch my next video for the continuation of this chapter. Thank you for watching. See you in the next video.